So I'm Greg Hura, and I've been working at SIBYLS Beamline for a few years. I thank all of you guys who came and attended. I really appreciate that, and everyone who's online. This is our first in-person user meeting in quite some time due to COVID. We really appreciate you guys coming. We've become a little troll-like in our behavior due to COVID, so hopefully don't scare you off. You guys are our community. We're very proud of you guys and the work you guys do. So this is back and forth. We hope you guys contribute to the discussion that we're going to hold today. And if you have questions, especially for those who are online, feel free, as you care to put your questions in chat. And we'll get to them at the end. Hopefully remind us to get it back at the end. And you can do that during the meeting. We prefer questions during the talks. This is a workshop. We'll cut our talks shorter if needed. It's very important for us to have a discussion. Let me get rid of this sidebar because that's a Zoom artifact here. There you go. And that didn't go away. Maybe it will. There it goes. All right, the screen's a little slower than my screen. All right, so a couple things I think. Yeah, so this workshop is around the SIBYLS Beamline. People who use the SIBYLS Beamline. SIBYLS stands for Structurally Integrated Biology for Life Sciences. It is now a fully SAXS Beamline. Where the "you are here" sign is where you are, right? Those of you who are here. And then all the way across the ring, which we'll visit today, is the SIBYLS Beamline. And this is an older slide. It's 1231 is the sector. It used to be both a macromolecular crystallography and a SAXS end station. And I kept the crystallography up there to remind me about how integral and important crystallography is. Also to remind me that the advanced light source, there's a lot of techniques here. So if you're only using the advanced light source for SAXS, you might be interested in all the other techniques that are around there, not just crystallography, but there's an infrared beamline, there's footprinting beamline, there's a tomography beamlines. So all of them are useful, and you can apply to them and use them in an integrated way. So today, this is sort of our schedule minus the coffee breaks and the lunch. So I'm speaking first. I've got a lot of the people who help run the Beamline are here. Some of them are speaking, some of them are not, but please feel free to ask questions. Following me, which I'll give a brief introduction. Let's see if I can get rid of this thing. That's annoying too. Wants me to join audio very badly. Oh, I don't know where. Yeah, here we go.
I've never seen that before.
Yeah.
All right. Unfortunately, I don't have our users' pictures up there, but users just are speaking to, and again, it's that feedback part. Mikkel will be talking later, so I got the star over next to him. Moving forward here. I can't proceed forward. There we go. Oh, now it goes all the way. So the screen is a little slower. Later in the day, you'll be hearing from Amici over here in the corner. Who helps with the SEC running. Nazar will be speaking, a newer postdoc, the newest member of our lab, later in the day. And then Josh Del Mundo, last of the speakers, last of the most organized session. The end of our session will be going through some troubleshooting, some hands-on work. It would be very valuable for us to hear from you about what you'd like to see in terms of analysis tools and discussions that we'd like to have during that time. And feel free free to put that in the chat or let yourself be known earlier. Okay, so I'm tasked a little bit with making sure that we're all talking about the same thing. So I'm going to do a little intro on the small angle X-ray scattering in general, very background. This is probably the most backgroundy section that we'll have. There is a bit of math, I'm warning you ahead of time, but probably the only piece of math you'll see all day. I don't know why I'm blocking that part of the screen, but let's see. I will drop my audio all the way down. And then there we go. So this is the typical SAXS setup. We've moved our sample to detector distance to 2 meters instead of 1.5 meters. You'll see that later today, but this is an older side. But generally, this is a very easy experiment. If you guys have run it, you guys have experienced it. You bring a sample, some small volume, 30 microliters, or you have it going through an SEC elution. You place that in front of a very bright beam, and the sample will scatter, generating a circularly symmetric image. Okay, and small angle X-ray scattering is a difference technique. It doesn't make a lot of sense without doing the difference. One of the reasons is because of the beam and the shadow around it. So you'll see a little darker image in the middle here. The beam itself is 10 to the 13th photons, whereas your signal may be a single photon, right? So this area is very, very bright, and we're looking right down the barrel of the beam. And so that sort of all the like tiny amounts of parasitic scattering that are coming off that aren't part of your signal, that has to be subtracted. So this is your sample. This is your buffer. When you subtract the two, you importantly get rid of this very dark, very bright area. So this is the scattering data is circularly symmetric. So if you just take a line from the center to the edge of the detector in any direction, that data should be equivalent. And the reason that we collect an area is because it gives you more signal to noise. So we basically just go around and just integrate all the way around, and we get this 1D plot here. Now, this is the sample in red here. This is your buffer in black here. The difference is what we're after, which is the green in this case. And you can see way out in the small angles, or the sort of higher angles, that the difference between your sample and your buffer is very tiny, almost imperceptible. And you only see it when you take the difference, and there's a big jump. So typically, again, very slow response from the movement here. There we go. And my audio thing's up again. You typically plot it on a log scale, okay? And that will mess with your general sensibilities, right? We don't think in log often, so things that you see, you have to understand that it's on a log scale, and it's these differences are very small. We plot the data as X-ray intensity, the intensity across, versus scattering angle, okay, theta. Now, we've manipulated theta to be Bragg law-like, okay? So we've manipulated it into a formula like this, and we've put the wavelength here that we're collecting at. So we're collecting at monochromatic X-rays, regardless of intensity, okay? But there's sort of a normalization that occurs. And there's, because of this, it's there. Oh, no, I've gone back and forth. All right, so what you're seeing here on the screen is a water strider. So scattering and diffraction are not 4 legs in. And when he jumps down, he creates these beautiful scattering profiles here, okay? So you can observe this in nature, and it's not what you would think. It's not just sort of a flat wave, but there's positives and negatives that create big intensities and low intensities, high points in the waves and low points in the waves, right? And the same is true for what we're doing, which is that usually what's really happening here is it's more like a plane wave walking around and hitting these four legs. We have a plane wave of X-rays coming in and hitting your molecule. And again, this is that Q thing. So the X-rays are going this way, they get diverted a little bit. So that is a transfer of momentum. And so this is, Q is also called momentum transfer. All right, everything scatters. Sorry, updating on the Zoom. Excellent. Everything absolutely scatters, right? So you stick your finger in the beam, it will scatter. And don't recommend that, but that will happen. So water will scatter. And if you look at the scattering from water and decompose the little different parts of it, there are the scattering from the individual atoms themselves, from oxygen and hydrogen. Then you have the sort of atomic stuff, which is the distance between the oxygen and the hydrogen distances. So that's the stuff that generally we're interested in small angle X-ray scattering, is this sort of middle term. But then later on, there's also particle interactions, so water molecule to water molecule to water molecule. And that organization of that sort of ice-like patterns and stuff will give you a very interesting scattering profile from just water itself. Okay, so this is the scattering profile of water itself. And so I've decomposed these little pieces, right? So there's the oxygen is here, then sort of the water term is the blue curve, and then sort of what takes over in water, or the organization of water molecules relative to one another. This is the black curve, and you can see that there's a huge change between them independently. So gas, water would look like this. Water looks like this black curve. And we're looking at the small angles. So we're looking just in this tiny, tiny region here where water is flat. And that's actually a useful definition of small angle X-ray scattering. Everything that's below the water ring would be what we were interested in. Really, small angle X-ray scattering comes from the small angle approximation. But now, in general, we're looking a little bit further where, the small angle approximation being that sine theta equals theta, we're a little bit further than that generally when we're analyzing our data. All right. So let's see. From a single molecule, I'll just use this one here. So if you're scattering from a single, let's see, this should be a movie. Let's see if it goes. I do not want to restart. No. Maybe it's on my end that it's being slow. Well, we'll see. My computer has decided to die. And hopefully I saved my last version of my talk so that it doesn't go into recovery mode. Sorry about that. Oh, stop. Be a copyright. Okay. Back. Where's the talk I was just giving? There it is. Share. Maybe it'll behave better. Share. I'm going to have to skip a little bit now because I'm a little bit behind. Let's see if this movie will play. It's really cool. Oh, it's just chunky. Anyway, if this is a picture of lysozyme, and if you were to hit this molecule with X-rays or neutrons, you would see this pattern here. And that's a lot of detail and information. And unfortunately, we're not doing this. Like the SIBYLS have attempted to do something like this. There's a lot of information in here, and we're of course just looking at this region here, but still a ton of information as you rotate lysozyme in. In our SAXS solutions, right, we are looking at every perspective of each of our molecules together, so you can think of it as a much more blurred version of this, right? This is now it's moving nicely. Oh, at least on my screen. All right, moving forward. I don't know what that's doing. All right. So this would be like the Ferrari if we were able to do this experiment where we could look at the single molecule. Unfortunately, we have scattering. Again, this is the averaging term. So you take the equations that you use where there's electron density involved and this Q factor involved, and these are all vectorial, and you get a vectorial 2D image. You are averaging over all of the electron density and all of its rotations. So this sort of triangular bracket hides an awful part of where we lose information. We're averaging around, and when you do that, you get this, instead of having this wonderful vectorial part where you can get all the distances between all the electrons and what direction they are, you end up non-vectorial, and you end up scalar. And so your intensity that we're measuring here now is related to the electron density in this equation, where all of this is in the P of R, okay? So you go back and forth from intensity to the P of R, there's a Fourier transform involved, okay? And I'll tell you a little bit about P of R in a second. So this is a toy system, okay? We have a triangle, we have atom 1, atom 2, atom 3, atom 4, and in solution, we have all of them in different representations. So that P of R function is how each atom is relative to one another, but binned on a histogram. So you know that from your P of R function, that Fourier transform to electron density, that the distance between atom 1 and 2, they show up as being populated, and it goes atom 1 to 2 and 2 to 1, so you get 2 of those. But you'll notice that atom 2 and 3, that distance between them is equal to the atom distance between 2 and 4. So they end up in the same bin in the P of R function. Again, we're losing that sort of directional information that we would have if we were able to collect just the molecule by itself. And you can see there's other distances that are the same over here. But this is the P of R function. And you'd say that's a lot less information. The beauty of SAXS is that when things change a little bit, it really affects the P of R function. So if you were to just take this one atom here, this fourth atom, and move it down, you would have this P of R function. If you moved it sort of diagonal, you would have this P of R function. New distances would be introduced, or vice versa. So it can be very sensitive to changes in atom position, which is really handy in a lot of the work that we are interested in doing. All right, and so that manifests itself in going from your SAXS profile of X-ray intensity versus momentum transfer. So these are very subtle conformational changes of one protein. So this protein has a cap. That cap can close. These are two domains. These domains can come closer together or further apart. And all 4 of those options put together give you 4 different scattering profiles. Okay, so just this cap closing will give you a different scattering profile and a different P of R function than if the domains were shifted. So it's very sensitive to changes in position. I'm moving a little faster because I know I'm late. Is there an equation in here? Yes. The other great thing is that you can go back and forth between your atomic model and your predicted scattering profile. So here's a protein system. This is, you can calculate the distance between all the atoms, that histogram of distances between the atoms, plug it into this equation and get your intensity. So this is here, how the scattering profile is changing with these atoms. So that allows you to play this game. So you might have an atomic model over here. You can calculate your intensity as a function of scattering angle. And then you can make your measurement, your SAXS measurement. And you can see that the dashed curve and the orange curve do not agree very well. So then you can modify your model and see if they agree better. I heard a voice. Oh, that was you. All right. How much information is there in a SAXS curve? Okay, so it's a lot less than crystallography. All right, so there is a program out there called Shannon, which does a Shannon channel analysis, and it will tell you that depending on the noise and depending on your molecule, you can get anywhere between 9 and 40 unique pieces of information. Okay, so that is absolutely not enough to reconstruct an atomic crystal structure or something like that, right? The number of parameters that you need to define lysozyme are in the thousands. Okay? You'll never get there with SAXS data that just has 8 to 40 pieces of information. So we just need to be humble about that and understand that. But that doesn't mean that, that doesn't mean all is lost. And this is the analogy I make, right? So generally you have some idea about what your molecule is. You generally know that you're got a lysozyme or a GROEL or whatever it is that you have. So the analogy here is cars, versus horses or whatever you're modeling, glasses, right? You want to input all the constraints you can, and that makes your SAXS data much more powerful, right? So if you know you're modeling a car, there are 40 constraints, right, that you can get from your SAXS data to constrain the dimensions. If you know you're already working on a car, that's very different from the important parameters of, let's say, glasses. Okay, so please, make sure that you're incorporating the data, the information you have. It's a set of constraints. All right. So what you'll be learning today a lot about, and this is an example of part 1, is the process of going from, like, say, an AlphaFold model or some model that you have, and creating your experiment and your model comparison, and then applying computational tools so that you get a more realistic, more solution-like behavior of your molecule. So instead of being the AlphaFold model for this molecule, which is a very compact, hard, tough, compact thing, in solution, it's very, domains, beads on the string kind of thing, with mostly separated, but some little compaction that occurs back and forth. All right, I got asked this 1,000 times at ACA about what would I do with SAXS that I can't do with cryo-EM by very prominent people, so I decided to put that on the slide and slap that down. And the blue ones are about the high throughput, and I'm running behind. So when you don't need ab initio structure, so we're not big fans of ab initio modeling in our group. And we know that they exist, that there's DAMF and other things, but that's like not taking the constraints you have. You know you're working on a car, please put that information in somehow rather than ab initio. So when you're not doing things ab initio, when you don't need to define everything from scratch, SAXS can be very powerful and fast. For smaller proteins, for flexible things, when your cryo-EM is putting it on a grid is biasing your results, or you're looking at one prominent conformation, which isn't the biological conformation. When you have transient states that you can't trap on the grid, for time-resolved experiments, to establish the best conditions for lower throughput techniques like cryo-EM, obviously in solution you can do temperature, salt, and pH changes. When you're binding metabolites, so if you have an ATP system, there's about 6 ATP analogs you want to test, right? ATP, ADP, things that are non-hydrolyzable. I mean, anything that binds ATP, you've got a set of experiments you'd like to do. When concentration-dependent effects are important, like let's say that you have a complex that only forms under high affinity, in cryo-EM, that thing might fall apart, right? So before you get it. And then there's all kinds of specific circumstances that your protein responds to pressure or is light activated or responds to temperature. All right, so I'll just briefly introduce our high throughput system. This is our high throughput system, which you'll see later today. What we've done is we've coupled a liquid handling robot to the brightness of an X-ray beam. And so you guys send us plates, and our liquid handling robot will pick up your sample, bring it right to the beam. The needle itself is X-ray transparent. So this is the needle, and there's a little window in it, and this is when it's landed in the X-ray beam, and X-rays shoot through it. Sometimes you'll see the damage on the X-ray beam in there as it's getting exposed. And then we generate our SAXS profiles for you. All right. Moving on further. Okay. So I think, unfortunately, due to timing, I probably have to end here. Catherine, is that right? 9 o'clock is when I was supposed to end?
Well, it's loose.
Yeah, but it's important here. So the future prospects for the high throughput system, we have till 2026 of June before the whole ALS shuts down, right? So we'll see how many of these things we get to before the shutdown occurs. But the number one thing that we really need to do to make the high throughput work better is the analysis. So we can generate hundreds of curves very quickly. That's great. And that now motivates the analysis, right? So I will go, or one of us will go down and generate 300 curves. So how do you analyze all that data? And we're doing that at an unprecedented rate. We really need to work on that. But other things that are coming up are the ability to collect from smaller volumes. So 10 microliters instead of 30 microliters. We would like to be able to rapidly replace our needles. So we have a sample oscillation. So when I'll have a slide on it, but being able to rapidly replace needles would really improve things. Brandon's introduced temperature control so that every time your needle lands with your sample in it, we can modify the temperature. So we can now collect at 4 degrees and collect at 80 degrees next. We can go quickly between the two. We can also do ramping of the temperature while the needle is in the sample cell place. So we can look at the temperature SAXS of, let's say, several mutants or similar like metabolites or things like that. And that's already in place, but we've only had one example of it so far. Multiple plates on a deck with a cover, and then there's this whole upgrade thing, which we're going to do in 2027. And I had a whole bunch of slides on each of these, but I will stop there and see if there are questions. Give a lot of intro about SAXS, but that's all you'll hear about the technique.
On the slide where you were talking about the benefits and the kind of the ideal use cases for SAXS, you had some of your bullet points were in blue and some were in red.
Yeah.
What was the difference?
The difference was these were the rest of the slides were about. I'll quickly go through temperature control, etc., and improved automation. So those were the rest of the talk, which I.
No, but
Yes.
The one slide you made.
Right. About the things that were coming.
No.
Oh, sorry.
People at the ACA asked you why would you use SAXS instead.
Yeah. Okay. Those were all high throughput.
The red ones.
The blue ones. Were all high throughput associated.